Hey everybody, welcome back. I do have a window open, which may be a bit unfortunate for streaming, for webcam. It doesn't seem too bad. Cool, so welcome back. We're going to be doing more of creating a NES emulator from scratch today, using Python 3. And today we're just going to continue doing all the things we've been working on recently, so particularly implementing all the instructions and getting things like addressing modes right for the CPU, which is a 6502. Yeah, so one of the main things I want to be working on today is, so at the moment we actually instantiate each one of these classes only once. So we're making each instruction is an object, but so there's no real cost, but people have been pointing out it's probably not a great way to do this. So we're going to turn all of these into just classes and use class methods everywhere. Yeah, exactly. Hopefully this will make it better. I'm going to rearrange some of this stuff as well. I have some ideas on how we can make this a bit nicer, but you know, you got to learn by doing. So let's do that. Let's learn by doing. So kind of what I want to be doing is turning this instruction class into something that we never really instantiate, because there's no real point, because we're not storing any state. There's no real need to make this makes this instantiated. Cool. So we now are going to turn everything into class methods, and from then on there, then we'll go and we'll implement some more of the addressing mix-ins, we'll write some more tests, and we'll write some more everything, basically. I might quickly close this. Give me a second. Perfect. All right. Let's keep going then. So we're going to turn all of these into class methods. The reason that we kind of want to do this is so that we, like I said, we don't have to instantiate anything. So we can just make an identifier byte equals to be none, because that'll make it a class property. Probably don't have to make this inherit from ABC anymore, which is an abstract base class. We're just going to do that. Right, so all these methods are going to stay the same, except they're now going to be class methods. And they're all going to take in class things. Whether or not this turns out to be a good idea or not, we will see pretty quickly. These could equally be static methods, I suppose, but, well, not this one. But I'm going to get rid of that. Boom! So, the reason that I'm doing this instead of making them all functions is perhaps a bad reason, but it's kind of, what we're going to end up doing here is very similar to using, passing around functions as objects and calling them. So kind of one of the reasons why I've talked about doing this is someone, Dan Tupp, has opened an issue on the GitHub page, which is pretty cool. And he also left a comment on one of the commits, which I can't actually find now. I've still got the email, though, so I can get it from there, but it's a bit weird that I can't see it anymore. Oh well. And he said there's a great test ROM called NES Test, which is linked on the wiki. It's a series of tests that are going to be useful for us, which sounds really awesome. NES Test, yeah. So we've got that. It's a series of tests that can be run automatically, but also interactively. You basically load the ROM, put the PC at C00, and then execute, logging your PC on every cycle and compare to a sample log. Cool. So this sounds like what we want to do as our way of testing out whether all the instructions have been implemented. So thank you very much for Dan Top. And he also left a comment, which, yeah, I can't find now, but exists somewhere, about passing through functions and how he's done it. And he's been doing the same thing. He's also been creating a NES emulator recently, but I think he's been doing it in C#. But it's pretty cool either way. So thank you, Dan. All right, let's keep going then. So we're just going to be converting everything to class methods for now. Cool. So one of his suggestions was that to just have the addressing mixins return a get. Trying to download PyCharm and stuff right now. Sounds awesome. I would highly recommend PyCharm. It's really, really nice once you get used to it. Cool. So we're going to turn all these mixins into classes as well. But potentially we might want them to just overwrite getAddress, and we'll have something else that can overwrite getData, which I think is a kind of a cool idea, but this is what I like about these mixins, is that they allow us to do a bit of different stuff. So we can overwrite getData where we want to, if that's what the addressing wants us to do. So we'll think about that. Anyway, so I'm going to go back to creating more mixin types. So we talked about mixin types last time, yesterday I suppose. And where are these mixin types? So I think it's on this page. Yeah, so we have immediate, zero page, absolute, indirect. Now, I believe 6502, there's a page by Skildrick, I believe, which is a 6502 disassembler, or assembler. And it seems a really good introduction to the language, so I'm going to be using that to do stuff. Going to buy a book tomorrow. I don't actually know many good Python beginner books, to be honest, off the top of my head. I'm sure they exist though. There's a really good Django book called Two Scoops of Django, but that's a bit down the road potentially, Senpai Velk. Alright, so we've implemented absolute addressing. Now we wanted to do absolute X and absolute Y. So that is basically go to an offset and then add the X register. Store the value of A in memory. Cool. So if we say a store A 1234, it's going to turn into 3412 because it's stored in little endian, and then we're going to add the value of whatever's in the X register, and that's going to get us our memory address. So the memory address function, what is this going to do? Oops, these should all be class methods. So the memory address is going to be getAddress. So this function has to return not only the value of 1234, but also what is in the CPU X register. So this is where it's going to get a little bit more confusing, because now to get the value of the X register, we actually need to pass in the CPU or do something similar to that so we can access it. Let's just think about that. So when it gets the data, we pass in the memory address. Interesting. Yeah, so we need to be able to resolve this. Alright, well let's just do it. Let's just do it and see. Later we can come back and change this if we decide it's a terrible idea. which is basically my general philosophy. Cool. So the only thing we're going to need to change in here is we're going to get the base address is going to be from the bytes, and it's going to be in little endian order. Boom. And so the address is going to equal base plus the value in the X register, which is going to be address equals the base address plus CPU.xreg. Again, we might do this through a mix-in later on, but for now, all of this will become more generic as we proceed. Cool. So what does this do? This returns the xreg. So what's the difference if we were going to do the yreg version? Would literally just be replace all the x's with y's. Now, as soon as we do that kind of copy and paste operation, the first thing that comes to my mind is, well, let's try and not doing it using a copy and paste then. Right, so how do we get the X missing? My PyCharm isn't finding the interpreter. Just quickly, Senpai, if you go to Preferences and then you go to your project, once you open your project, Project Interpreter, and there should be a drop down of all your Python environments here. And there's also a way to add local, and you can just navigate to wherever it's stored. There should be documentation and stuff on that, but that's how you do it really quickly. Alright, cool. So absolute addressing with X mixin. And this is absolute addressing. Now, is there any way we can genericize this and have it so that this class is going to get... screw it. Let's just leave it for now. We can come back and make it nice later. Since we only have to implement these once, it's actually not going to be too bad. Alright, let's go back to 6502. What are our other types? So, zero page. I don't actually know what zero page is, so let's find out. So, all instructions that support absolute addressing. Cool. With the exception of jump instructions. Fair enough. Also have the option to take a single byte address. Right, so an absolute takes a 2-byte address, which means it can access anywhere in memory, because you can go between 0 and 65,000. This type of addressing is called zero page. Only the first page, the first 256 bytes of memory is accessible. Whereas if you go to absolute, you can hit the first 65,000 bytes. This is faster as only 1 byte needs to be looked up and takes up less space in the assembled code as well. Cool, that's really smart. So you can quickly and easily access the first page of memory, which is going to be a pretty common operation. Let me see. Zero page X, this is where it gets interesting. Okay. So if we load 1 into X, we load a hex value into A, and then we store at A0 plus 1, increment X, store at A0 plus 2. Cool. If the result of the addition is larger than a single byte, the address wraps around. For example, if we overlap, then we want to overlap. So let's implement that as well. Let's implement an overlap. Let's see if we can do this. So class, what was that called? Zero page. Zero page addressing mixin. Comes from the addressing mixin. And it's going to look up an absolute memory address, but only in the first 256 bytes. So the example is going to be store A 12. The memory address will be 12. Cool. So the data length here is only going to be 1, which is why the 0 page appears to exist, so that we can have this smaller operation. Welcome back, the real Lemon. So I started learning variables, strings, floating points and stuff today. So far so good. Awesome. One thing I recommend if you're starting off is just little simple games are really good to start. Nothing to do with like graphics or anything, but just like, hey, try and figure out something where you can have a store that has items in stock and you can buy something from the store and then sell it to someone else, or whatever. That makes it's basically introduces you to all the things you need to know to do programming, and it's kind of fun when you can have something where you can play around with it a bit. Alright, so again here, the data bytes that we're going to get in is actually, since the address is only going to be 1, we actually just need to return the data bytes. The byte order is not going to matter because there's only going to be a single byte, but that's fine. Cool. Alright, what happens when we do the X page? Literally not in the drop down, I can't find it. Okay. So this button here will allow you to add things to that drop down menu. It depends what operating system you're on, but I would search how to install Python properly because it should come up in those drop downs. If it doesn't, then you have to go to where you have installed it and find the Python bin file. Yeah, messing around, creating calculators and stuff is good, but I find, personally, it's a lot more fun to create a game than it is to create a calculator. Well, for me, at least. They're kind of a bit more entertaining to mess around with. So store at 12 would return 12 plus the X register. Note, will overflow. Can overflow. I don't think I know how to make a game yet. Yep, sure. Keep doing what you're doing when you do it. Ambition is good. Oh, might be. We'll see if this project works out. Cool, alright, so the base address is going to be whatever it is, somewhere in the first 256 bytes. And then we want to return the X register. Now, we also want to check if this is going to overflow. Which it might. Yeah. Now, kind of one thing that we notice here is all these things have a very common pattern, where this is actually exactly the same code as what we've got here. This one might add overflow detection or something, but whatever. They're getting past the Y-reg and the base address and all this kind of stuff. So, look, while we're here, let's try and genericize it. So to start off with, we've got an absolute addressing mixin. Cool, so that stays the same. What we're actually adding though is something where we add the X or the Y register to the address. So let's try and make that as a mixin. Yeah. So it's going to be an addressing mixin. And it's going to be a X reg addressing mixin. Let's call it that. Let's make it inherit from object. So we're going to try and do this now, and we'll see how it works. So basically what we want this thing to do is to return the value of the X register when queried. And really what this is going to define is an offset, because that's what the X and the Y, they're doing an offset in the memory location. So I think I might just make the addressing mixin Might make this a class property, so it should just be data length plus 1 is instruction length. And it should also have a class method, which is going to get the offset. And by default, it's going to return 0. What is a class? That is a great question. I probably can't explain that easily. There are plenty of good tutorials on what classes are and how they fit, but the answer is it's basically a way of wrapping a collection of functions and storing state about that object. So creating objects that have a collection of functions and state and stuff. If those words don't make sense, then yeah, I can't really go back too much further than that. Well, indeed. Yeah, that's a pretty that's a tricky one, to be honest. All right, so our xreg addressing mixin is just going to return the cpu.xreg. Hello, QGLS. Do you have any tips for small projects I could start? I spend an hour or two writing not notes, blah, blah, blah. Yeah, I was just saying before, I think that writing a small game is always super fun and a pretty easy thing because you can make it as simple as you want. So you don't even have to get user input. It could just be, hey, store a list of items and, you know, buy and sell them and make their price change, something like that. Yeah, that's a really good answer, Cadex. That's way better than what I said. Alright, so a Y addressing mixin is going to return our Y register. Cool. Absolute addressing mixin. So our absolute addressing mixin is going to return the base address. It's going to have a data length of 2. Return this, and I might just say plus class dot get offset CPU. Right, so our base absolute addressing will just return the value and any offset, which is going to be defaulted to 0. And then if we want to just add in now the X mixin, we can just define it as an absolute addressing mixin along with an xreg addressing mixin. Cool, so now these names are starting to get a little verbose, so let's kind of cut them down. Cool, you recently made a Chip 8 emulator HTML5 now making game BA. 35 opcodes. Yeah, I actually, so like I said, I've never really made an emulator before, but I decided I'd try and jump into it and, you know, see what happens, basically. So I've never done a Chip 8 or a GBA. That's awesome. I drizzle / let's get a / horde going. There we go. Alright, cool. So now we've got xreg offset. So I'm going to call this an xreg offset. I'm going to call this a yreg offset. So now we kind of know that, and this is going to be I'm just going to call this addressing. Yeah, I'm going to rename everything. So basically, you can have no addressing, which is a type of addressing. You can have immediate read, which is a type of addressing. You can have absolute addressing. And then we're going to have absolute addressing X offset, which is going to be an xreg offset. I don't think these things actually need to Actually, I think I can just do that. Yeah. Is Ruby similar to Python? Relatively. I've actually done a lot of Ruby as well. In terms of similar languages, they're very similar languages, but you will find a decent amount of differences between them, obviously. Cool, so now we can just define an absolute addressing with an X offset as a collection of these mixins, which is kind of what I wanted to do, is to build this kind of stuff through composition, which I think is pretty cool. I don't know if it's a good idea. Let's find out. Let's do the same thing for zero page. So zero page is going to have to return. So zero page is actually going to do the same thing, but the exception is it's going to have to do some overflow checking. We're going to assume that absolute addressing can't overflow. That might be wrong though. Anyway, so the address is going to be this, and now we've got to check for overflow. Note can overflow. So if the address is greater than, so the maximum value is going to be 255. So if the address is greater than or equal to 256, we'll just do address equals address mod 256, which should make it a value between 0 and 256, unless I'm wrong with that math. But we can pretty easily check that. Anybody currently using Python for aside from this emulator? Mainly this emulator, and I also do Django development. So Django's a web framework that's in Python, which is really cool. I've started using recently, and so I'm making some software with that. I used to work as a Python developer as well, so, but I don't anymore. Fixed it. Good work, Senpai Valk. Welcome to the world of Python. So again, now with a zero page addressing with X, we can just add a X reg offset to zero page addressing, and now we can just build it through composition. Isn't that cool? So adds the X reg offset to an absolute memory address, and it's still got to be in the first 256 bytes. Why? So this is kind of what I was talking about, KDX, where I kind of wanted to make this a bit more, bit cleaner, a bit nicer. Some people might dispute whether that is the case, but screw 'em. Alright, let's go. So we now have all these different types of addressing. Are there any more types of addressing? So we've done absolute, we've done zero page, we've done zero page X, we've done zero page Y, we've done absolute X and absolute Y. We just did immediate, and there are a couple more actually. Oh, there's like way more. Oh, jeez. Alright, well, let's keep going then. So we got relative. So relative addressing is used for branching instructions. These instructions take a single byte, which is used as an offset from the following instruction. Okay. So it only takes a single byte, whereas, so much like zero page addressing, it takes a single byte. And it's going to return something which is relative to the current program counter of the PC. Now we might get an off by one error here. I'll have to think about how that's going to work. Love the stream. Thank you, Brad. I appreciate that. An emulator Dave stream? That is awesome. I think so too, Anti-Pixel Studios. Yeah, like I said, we'll see whether it works out. Alright, relative is going to be C0 or labels. I don't think we have labels, so we're just going to use it as a relative. So let's do it. Yeah, for anyone that's interested in following along, like I said, all the episodes are up on YouTube, and particularly the code is on GitHub, and it's all open source, so feel free to grab it, branch it, do whatever you want with it. Not that there's many real applications of this. To be honest, people have already probably done this a lot better than I have, but they haven't had as much fun as I've had. Maybe. Alright, convert docstring. So relative addressing is going to jump to an... Yeah, okay. Offset from current program counter. Cool, I think. So I believe that the relative is going to offset from the current program counter. And offset from the following instruction. Yeah, so let's do a step. So we load 1. I'm just going to see how this thing works. Compare to 2. So compare is a thing. Branch to not equal. Yeah, he's going to chuck us down to here. Okay. I'm learning Python. Is this the full version of PyCharm? This is the full version of PyCharm. I have the JetBrains toolbox or whatever it's called, which I bought for some other stuff, but obviously I really enjoy using the full version. But to be honest, unless you're doing Django development and stuff like that, you probably don't need the full development. The community edition is really good. I made a Java Game Boy in Java. That was seriously fun. That's awesome. I'm a big fan of these kind of projects. They're really fun. Java? Fun? Nah, Java's not too bad. Alright, so this is actually just an addressing type. It's going to have a data length of 1, so you can only jump 256 bytes. Oh, it's probably signed. Is it signed? Maybe you can only jump 128 bytes. Maybe not. I'm going to put that as a to-do. Is everything signed? Oh god. This is one of those questions like whether this thing has a pipeline or not. I just don't know. Yeah, 100% the community edition is all you need. The functionality that it adds in this is pretty much only for the web stuff. You don't need it. Alright, so our address is actually... Relative addressing. So we're going to need to get the program counter and then offset from that. This might cause an off by 1 error. And the reason for that is potentially this is going to tell you the offset from the current instruction, and it might need to be +1 or something depending on how this is implemented. But I'm sure that the NES test ROM will tell us that. Cool. So the program counter, or let's just call this the current address of where we're executing the program, is going to be the CPU.PCReg, whatever value's in there. And then offset by the value in the instruction. So the address is going to be the current address. So we can just return this. So we can just return the current address plus whatever is stored in the instruction. Thank you, Brad. Yeah, I try to just kind of talk through what's going through my head when I'm doing anything. I tend to ramble a bit, but I think that's kind of good. Just get you a bit of an idea. Yeah, if you have any feedback or anything like that, I'd love to hear it and how I could maybe do things better. I tend to say what I'm typing a lot of the time, which potentially isn't the most useful thing, but oh well. Alright, we've got relative addressing. Awesome. Whether or not it is going to work or not. Cool. Implicit addressing. Some instructions don't deal with memory locations. These are said to have implicit addressing. The argument is supplied by the instruction. So we have called that no addressing. Technically, this should be called implicit. Cool, so an implicit thing is it doesn't actually need to deal with a memory location. So we don't care. This should just be called immediate addressing. That's great. Awesome. Thanks, bro. Indirect. Indirect uses an absolute address to look up another address. Haha, this is where we start getting fun. So the first address gives the least significant byte of the address, and the following byte gives the most significant byte. Right, so that's just another way of saying it's in little endian mode. That can be hard to wrap your head around. No, that hopefully is what I think it is. Alright. The instruction jump causes the processor to look up the 2 bytes at F0 and F1 and put them together. Oh, okay. Yeah. So the first address gives... Right. Okay, so this is where it's going to get a little bit interesting, but I think we can do this. So class indirect. Indirect addressing. So what this is trying to say is it's going to pass us in a memory address, and then we're going to use that memory address to look up another memory address, but we also got to remember to turn that into little endian mode, which is fun. So what it's telling us is that the first address is actually just an absolute address. So what I'm going to make this do is something kind of dodgy here, is I'm going to make this inherit from absolute addressing. And since it inherits from the absolute thing, when we can override the address, we can call super. Can you call super on a class method? Cool. So we will get back this is going to be the original address that the instruction is referencing, right? So we're calling the super of absolute addressing. So we're telling absolute addressing, look at this instruction and tell me what address it's referring to. And then this instruction is going to look at what is in that data byte and turn that into another address and return that instead. How often do I typically stream? Well, this is my 4th stream, and I've been doing it for around a week now. So I would say, yeah, a couple of times a week. My first time in the stream, you've already made the registers in the APU. I have not made the APU yet. That's for sure. I've mainly been working on the CPU and implementing all the different kinds of instructions and loading in ROMs. I've kind of got the framework for PPUs and for APUs set up. But you can see they're just kind of like dumb memory objects at the moment that can own memory and write and read and that kind of stuff. So yeah, it's going well though. Alright, original address is that, and so we want to look up the bytes at the original address and also the one that's at the original address plus 1. Cool. So the best advice is make a memory view for debugging. That is good advice. I will do that. So the least significant byte is going to be CPU dot get memory owner. So this is something that we kind of commonly do, is this. Hey, ask the CPU who owns this bit of memory and ask them to get or to set it. So I might just create a helper method in the CPU. So to basically to get a piece of memory, and it's going to just route it through to the correct component. So yeah, let's just say get memory for now. And it's going to pass in a location, which is going to be an int. Another thing I'm doing is Python 3, these new type hintings. So, you know, I'll do them every now and then. Cool, so we want the get memory function to just return a piece of data. So returns a byte from a given memory location. And these bytes are actually just going to, we store bytes as ints. All our memory devices, like the ROM or anything, actually just returns ints. So they store things as ints, not as bytes. Could I still make a game on an application? Absolutely. You can, anything you want to do, with the probably exception of web development using Django, you can do it in PyCharm Community Edition. I used to use it, and it's got pretty much, pretty much everything. Yeah, absolutely. Use it. Cool. So it's going to do all these things that we commonly do here. So it's going to find who owns that bit of memory. And it's going to return that byte. Cool. So now back in here, we actually just want to say the least significant bit is the CPU dot get memory at the original address. So this is going to return us the least significant byte. Good for learning. I'm very new to programming. I want to be good like you. I don't know if I'm good. You can always learn more. Is the answer. So I'm actually going to call this the least significant bit location. I'm going to also say what is the most significant bit location is going to be that +1. Yeah. I would highly recommend PyCharm Community Edition. It is all you need, and it's really good. It really helps you learn, I think. Cool. So we now, oops, that says MST, not MSB. So we now have our least significant bit and our most significant bit, and these are both integers. And I'm just going to annotate that here so I can remember it later on, because sometimes it gets a bit confusing about whether I'm talking about bytes or ints. And what indirect addressing hopefully is going to want to do is take those bytes, that LSB and that MSB, and then turn that into an address, and then return that address. So it actually just wants to return MSB plus LSB. Now, since these are both ints, this is not what I want. But this is essentially what we want it to do, is to return whatever the address is for this. So how are we possibly going to concat? So just looking back here, it's going to return. So if these are, for instance, 20 and 30, we actually want it to return 3020. Now the problem is what I'm talking about here is in hex. I mean, we need to actually flip them in hex or in bytes. God. So how do we normally do that? So int dot from bytes, and we flip the byte order. Here we actually kind of want to, let me think about this. we kind of want to convert these integers into bytes, and then turn it back into an int. I'm excuse me. This might be a terrible, terrible way of doing it, but it's what I'm going to do. Right, so the LSB byte is going to be a bytes. Yeah. So the address in bytes is going to be bytes of the MSB and then the LSB. And then we just want to return that. I think that's what it is. In addressing.py, does super run the super class constructor, or does it only reference the super instance? The latter would be a weird syntax of the form, be weird code. So I'm hoping that it calls the parent's class method get address, but I don't actually know. Yeah, let's find out, shall we? Yeah, this is where I use the super. So I want to test this out. So let's say indirect addressing is going to be a subset of absolute addressing. So let's pretend in our CPU that when we get past an absolute addressing, let's say that this STA absolute instruction is actually going to be indirect addressing. And so that way this code is going to get run. And let's see what happens when we do this. And let's see what happens when super gets called. Alright, what's going on here? Class takes 2 things, but 3 were given. Yeah, it would, wouldn't it? CPU. Boom. Apply side effects. Missing 1 positional argument. So apply side effects is a class method. Yeah, okay. So I haven't updated any of this stuff. This is just kind of the leftover from the refactoring that I was doing before that will, now come back to haunt me briefly. Alright, cop that, Python. Let's see what you got. Index is out of range. Perfect. Alright, immediate addressing. Data bytes 0. Well, that's weird. So data bytes is empty? Where's data bytes empty? Where are we coming from? What's our memory address? Have we broken something? Memory address is none. Fair enough. What's the instruction that I'm executing? An LDA immediate instruction, which uses immediate addressing. Where is immediate addressing? Here? Yep. An instruction. Okay. So it's going to call class.getAddress. Oh, can you not overwrite class methods? Let's look that up. I might need to change back to objects, which doesn't really bother me, because as long as you only construct the object once, it's not going to have any performance issues. I think it's weird syntax. Super doesn't seem an actual invocation, but it's just a reference to what other languages just call super. Yeah, I don't actually know. Let's look it up. Supering a class method. Cool. Yep, so you can just call super dot do your stuff. So it appears to be the super this just returns you your parent either class or self object. In Python 3, I think it should be smart enough to figure out which super to call. But you could also call it with the manual arguments. Super in Python 3 would then be super.init or something. No, super is still just the reference to either your parent class or parent object. So I'm going to do it explicitly here to give, I think, what I'm trying to say. So if I do this, this is going to return the parent class of me, which is absolute addressing, whereas if I put self in here, it would return the parent object. Hopefully that makes sense. Let's put a breakpoint here. Let's see what it actually gets stepped into. So SCI, CLD. So LDA, which function actually gets executed here? Get address, CPU, right. So even though we are an LDA instruction, which means we're made up of immediate addressing, our get address, yeah, it's immediate addressing, so get address should be none. Well, that makes sense. All right. And then the value should be data byte 0, and data byte 0 is empty. Right, so why is data byte 0 empty? Funky. Instruction length. Aha! So this is why I had this be a function. Okay. So because this instruction length, when you're constructing the class, reads in data length, and then even if you override it down here, isn't going to change it. Okay. Def get instruction length. And it's going to return class.data length plus 1. So this will mean that we're no longer always going to have an instruction length of 1, we're going to have a variable instruction length. The problem being now, obviously, that those things that we're using that, which I probably should have found beforehand. Here, instruction.get instruction length. And in fact, instead of saying get instruction length, I can just call it instruction.data length. I'll just push this to over here. Cool, so we didn't actually need that. And the instruction length, so the PC reg should be get instruction length. Cool. One bug down. Do we have any more to go? Almost certainly. Cool, so the data bytes, we're now getting our data bytes back. Sweet. Sweet, sweet, sweet. So what happens now? We're in an STI absolute, but we're actually using indirect addressing. So I wanted to do this so I could see what happens when I step in here. So when I step in here, what should happen is the next line that should be executed is that it should call the parent, i.e. absolute addressings, get address function. So let's see if that's what happens. Absolute addressings, get address function. Yeah, it does. So I think the answer to your question, KDX, is that super can return the parent class or the parent object depending on how you invoke it. And I believe in Python 3, I'm going to do the same thing here, where I come back to this point. If you don't pass in any arguments, it will implicitly figure out which one to call. Maybe. Will it? Yeah. This is the class method. Yeah, so it's just a reference to your parent when you're doing inheritance, if that makes sense. Cool, so it appears like that's working. So we now have an LSB of... Oh, so we have an LSB location of 8192, which is 0xF... No, 0x2000. Yeah. Cool. And our MSB is going to be one above that. Now, I believe that these should both be... Oh no, one of them should be 16. LSB and MSB. Oh no, because this is the instruction. Anyway, I think this is working. So what I'm saying is if I have, hypothetically, a LSB that is 0x20, and I have an MXB that is 0x30, really MSB should be 0x30. So in memory, it will look like 0x2030. And what we want it to look like is this, and we want to flip it. So we want to make it look like 0x3020, which should equal 12320. And does this do this? Equals 48. No. But I suppose that's fine. And the answer is... Okay. We want to cast that back to an int. Okay. So int dot from bytes the bytes. And then we'll do byte order little endian. We'll pass it in LSB MSB. Does this return the correct thing? Yeah. If LXB was 0x20, the MSB 0x30. Yeah, that does return the correct thing. So this is going to work. Hello, TuxeNet. Welcome. Thank you for coming along. And thank you for the welcome drizzle. Alright, cool. This works. Let's never test it and pretend that this is perfect. Like all good code. Alright. What do we got going on here? Check if ROM can't order int and bytes. So we're getting a bytes value back from somewhere. Right. Int and bytes. So location is a bytes. So wherever I recently started calling location, here. So I'm passing in bytes here, presumably, when I should be passing in an int. I'm surprised at that. Because... So this is what Python type hinting should be called for. Because I can now say import CPU as C. And say that this is actually a CPU. And now CPU.getMemory self.location should warn me that this is wrong because LSB location. If I say that this is a type bytes. No. Is it? Oh no, these are both ints. Never mind me. Whoa. Did that just work then? That did work. What was I doing wrong before? Well, that's a bug that I'll never find again. Cool. Alright. Let's pretend that that didn't happen. Cool. Next step. Let's come back to here and let's say that this is not actually an indirect addressing because it's not. It's just absolute addressing. So if we now implemented all our types of addressing, and to go back to what I was saying earlier, this was kind of why I wanted to do everything as these kind of mix-ins, was because so I could just use composition to make everything up. So an absolute addressing with an X offset can just combine an X reg offset with absolute addressing and get that functionality. Or indirect addressing, to get the original address, I don't need to do anything apart from inherit. You can do most of this stuff with functions, obviously, but I just kind of like the way this compositional class way works. Cool. No. Did I close this page? Yeah, I did. Okay. What else have we got? Immediate, relative, implicit, indirect. Boom. We just implemented indirect. Indexed indirect. Okay. Now you're having fun with me. This one's kind of weird. It's a cross between the 0-page X and indirect. Basically, you take the 0-page address, which we've... Okay. The 0-page address. So indirect takes 4 bytes, whereas indexed indirect is essentially inherits from 0-page, so it only takes in 1 byte, and then you add the value of X to it, and then you use that to look up a 2-byte address. What are you trying to do? I am creating a NES emulator. Assuming that you know the NES console, but one of the original Nintendo consoles, and so using Python to create something that can simulate being the hardware that ran a NES. And so we can run ROMs and games and stuff that were written for the original NES. Cool. Indexed indirect. Holy crap, versus indirect indexed? Oh man. That's just crazy. Alright. Indexed indirect. We're going to have to be careful about which ones we use here because I feel like this is going to come back. Indexed indirect. Let's just say it inherits some addressing at the moment. Nice, thank you. Yeah, it's been going well. I've never written an emulator before, so this is going to be my first try. Cool. Okay. Take a 0-page address, add the value of X to it, and then use that to look up a 2-page byte. Oh my god. Okay. So, take a single byte address, add the X register, and then use that Now this is just going to be composed of functionality that we've written before. So we're just going to steal things and cheat basically. So what this actually is the first mode of looking up something is actually from 0-page addressing. And it actually is 0-page addressing with the X register, right? So you take the 0-page address and you add the value of register X to it. Yeah, so if we use 0-page addressing with X, in the same way that we used absolute addressing here, we can just get the same thing. And it's actually just going to be pretty much the same functionality that we had back here, with the exception of def get address. Gotta make sure it's a class method. It's actually going to be the exact same thing, right? With the exception of, instead of inheriting from absolute, we actually want to inherit from 0-page addressing with X. So, let's make both of these things inherit from the same base, and then just reuse the code again. Again, just like finding where there's common ground, pushing that up a tree, and, you know, making everything nice and reusable. So these, what's the thing these are all in common? These are all indirect typed, and they're all in different ways, but they share a common thing of being indirect. Cool. Jeez, this is getting out of hand. Oh well. So indirect is going to have a getAddress function. And basically we want it to call the super.getAddress of whatever type of addressing you want to inherit from. Yeah. So basically I want to genericize this code here, because this code is the crazy stuff. So we want to get the address and then pass it to a function or something. So indirect, and we're going to say, just have a class method here that's going to get indirect address, and it's going to take in a base address parameter. So we're going to presume that the base address is passed into us. Yeah, there we go. And then yeah, okay. Instead of doing that, wonder if there's a way to do this smarter. I mean, basically what this is now is a function, this little thing here. So I can just pass this in as a function, probably makes more sense. Alternatively, I could make them inherit from something. It's going to get a little bit complicated. So I might just make this a function. That's just going to get an indirect address from something. LSB location equals this, and then we can just say return get indirect address CPU LSB location. Yeah. Alright, so this becomes our thing. So now indirect addressing versus indirect indexed, or is it indexed indirect? Kill me. Indexed indirect. Because they couldn't be bothered coming up with unique names. Indirect actually just inherits from zero page addressing with X. So this will get you your zero page addressing with X, and then you can just pass it through to this function, get indirect address. Yeah. Yeah, sure. Alright, and then lastly we're going to have indirect indexed, and this is going to be our last thing. Which is just going to do NAS. Oh. Yeah, this is going to be interesting. Oh, let's do it. Indirect indexed. Indexed indirect. Indirect indexed. Indirect indexed is like indexed indirect but less insane. I'll believe when I say it. Instead of adding the X register to the address before dereferencing, the zero page index is dereferenced and the Y register is added to the resulting address. Oh my god, for real? Okay. So we just use a typical zero page addressing to find the original address, and then we add the Y register to the result afterwards. And so how do we add the Y register to the result? Yeah, so we're just going to compose it. So we say it's got a Y reg offset, and we just say return the indirect address of that, of the thing that comes from the 0 page, and then add self.class.getOffset. CPU. Cool. So I believe that's actually it. That's actually all our indexing modes. Now, whether they all work or not is, you know, questionable. Let's put it that way. But I think that's pretty cool. Now, my only thought is that these all use the same kind of code here. So can we genericize this to put this into an indirect mix in, which we can then add in? And the indirect thing, so these all, yeah, yeah, the regex is not going to be fun. Indirect indexing versus indirect, oh god, index indirect addressing. It's tongue twisters all the way down. So these already inherit from things that provide our address functionality. So we can call super, and then really we want something that can just call this and return get offset. Because all these codes should be exactly the same. Yeah, screw it. So let's do it. We've done it this way everywhere else. Indirect. So depending on the method resolution order here, it's either going to return, it's going to call, if I have this function in here, there's going to be some weird stuff going on. So when I call getAddress, it's going to call this one unless I call super, and this can't call super. So it's going to have to be a different function. So I think, yeah, potentially this should inherit from, maybe I'm going crazy here, but if we make this inherit from addressing, and then we say this code is this, so it's got to be the LSB, and then return yourself, and then we can just compose out of what kind of thing we want. And this super.getAddress can come from a different composition. Yeah, I think this is going to work. And then we can pull this out of the function. We can shove this back in here. Boom. So switch the bytes and then plus the get offset from the CPU. Get indirect address can disappear. I've added this to the wrong class. Yep, okay. Sounds like something I would do. Holy crap. Okay. Add this to indirect. Alright. Let's go. No stopping us now. So we have an indirect method, an indirect class, which is going to get the address from whatever is the parent addressing. It's going to get the MSB, it's going to get the memory at those locations, it's going to flip them, and then it's going to add any offset that's necessary. So here's the cool thing. Now if we want to make indirect addressing, I'm going to call this indirect base. So now indirect addressing actually inherits from indirect base and mixes in the components from absolute addressing. Actually, it's meant to be the other way around, I think. Warm. Alright, so, indirect addressing, whatever. So this will now call indirect bases. When someone calls get address on this, it will go to the get address of indirect base. And I believe when the super gets called, it should call the get address of absolute addressing due to the way that the method resolution order happens. Whether or not, this works or not, let's find out. Okay, let's see what happens. Let's put a breakpoint here and let's follow. Cannot import name. Fair enough. I believe that. STA absolute instruction doesn't exist. Oops. I don't know how I did that. Renaming something. Alright. Cool. So we're executing SCI, whatever, CLD. When we get to the STA absolute, which we're not quite at yet, now we're at. We want to step into the memory address, the get address function. We want to find out where it goes. So it's calling indirect addressing, and I'm pretty sure it should go to indirect base, and then it should, we'll see. Yeah, so it goes to the class method of indirect base, and then it's going to call super.getAddress, and I actually want it to get the address from absolute addressing. So does it go there? Cool. Which returns plus an offset, which doesn't have any. Or this class.getOffset might be an issue actually. This is interesting, basically writing a VM. Yeah, I mean, essentially. VMs are, yeah. This is more, I guess maybe this is what is happening in a VM. My suspicion is this is more emulating hardware, whereas a VM is probably more emulating the operating system stuff, but I actually have no idea. You're probably right. Interpreter, in a sense. Yeah, at the moment this is an interpreter. So this is a interpreter for a CPU, the CPU that's in the NES. Hence all the CPU things everywhere. God. Alright, so the offset is 0 for this. What's the next line executed? Get offset 0. Return. So the LSB location is 8192. Like we expect. It's going to find what's at 8192. It's going to return that. It's going to get that memory. Yep. LSB, MSB. Cool, so LSB is 0, MSB is 0, perhaps not. Unsurprisingly, it's going to flip them, and class.getOffset is still going to be 0. Now, my concern here, this is in indirect addressing, is when we use 0 page addressing with X. What happens if we do that? I'm just going to do that, because I get the feeling this might be a bug. That the class.getOffset is going to be returned the wrong thing. Indirect, indexed indirect, holy shit. So this adds the xreg before indirection. Holy moly, alright. So let's make it this STA absolute one of these instead. This is just kind of like my test instruction. And let's see what path this actually takes. LDA, right, step in. Boom, so we're in 0 page addressing. And so we should be in 0 page addressing with X, and 0 page addressing with X is just 0 page addressing combined with the xreg offset. So it should be find the absolute instruction and add whatever's in the X register to get the indirect memory location. Holy moly. Alright, so class.getOffset is 0 xreg Right, and CPU.xreg is equal to 0. Okay, yep. So it does get the xreg's value, and then that's going to be fine. Alright, I'm going to redo that again because I went too far. Cool, so it's just going to get 0 page addressings. The reason is I haven't inherited indirect base here. So now when I do it, let's step in and let's see. So now when we call the indirect base, it says, give me the offset, give me the address. And so it'll come down here to 0 page addressing and it'll call class.getOffset. So now where does this class.getOffset go? It goes to xreg, which is what we want. This is going to return. And now when we go down to here and say class.getOffset, this should actually not go to xreg. This should go back to none. Yeah, and it doesn't. So the way that what we're going to have to do here is we're going to have to say def get offset, which is a class method, and we're going to have to redefine that. Return 0. Cool. So now by default, it will call this return 0. That's some devious things going on here. Alright, so step in, getting the offset. No, that didn't work, so it's going to come back to here. Right, so indirect base shouldn't define it. So what we're trying to say is indirect addressing is fine. This indexed indirect is going to have to come from indirect. Then you want to get a 0 page addressing with X before, so that'll work. And then when you come back here, this is also going to be the xreg, which we don't want. So this is the issue here. Because we re-override the same method twice. So it's kind of when we want it, we want this to call its xreg offset. We want this class.getOffset. This is breaking my brain. Alright, I might leave this to do bug with get offset being reused. Adds the yreg after indirection. So it should use 0 page addressing, then indirect it, and then add y. Whereas this one should use 0 page addressing, and then just indirect it with X, and then indirect it. But there's a little bug there. Anyway, I'll fix that later. Cool. what do we want to do now? We want to make this the right thing, so we want to make this absolute interesting. So what I was kind of hoping to do now was, now that we've quote-unquote done with addressing, is let's turn back to our instructions and let's create some generic instruction stuff. Can you give an overview where you are right now with building the emulator? Yeah, why not? Sketch. Let me just plug this in. Sorry. Cool. All right. So this is just going to be a quick overview of where this thing's at. So building an NES emulator. So if this is the NES is going to be made up of several components. So what we're doing at the moment is the CPU. Then there's going to be other stuff over here, which are your other components. So your PPU, which is essentially your graphics card. Your APU, which is your sound card. And, you know, your memory down here. So your RAM. And then over here, it's the game code or the whatever you want to read in, which is called your ROM, so your cartridge. So the idea kind of is that this ROM component has already been written by people at, you know, wherever, Nintendo or something, 30 years ago. So that's actually fine. Tick. The CPU, this is what we're working on at the moment. And that's, you know, it's got a fair way to go, but once we implement all the instructions and stuff like that, that'll be a big chunk of it. We'll need to do a debugger and other stuff, but you know, this is on the way. This is in progress. The RAM, I'll need to create a debugger for this, but I think at its core it's just storing values, so it's probably, you know, reasonably done-ish. The PPU and the APU are not started. Yeah. So I'll call this done, this ROM. I mean, that's pretty much the overview. So we're focusing on the CPU at the moment. We haven't started the PPU and the APU. The ROM is done through no work of my own, and the RAM is, you know, well, I can't think of anything we'll really need to do for it. So, yeah, that's kind of a basic overview of what we're working on in the system at the moment and what's left. The Destroyer, Greg. There you go. Hopefully that made sense. All right. So what I kind of want to do is we've now got something that can genericize this addressing type. Now I want something that can genericize this LDA type. So an LDA thing is always going to do the same stuff, right? Cool. So let's do that. So an LDA instruction is probably going to inherit from, let's just say it inherits from object for now. And it's just going to overwrite our write function and say cpu.areg equals value. So if you think about it, every LDA instruction is going to do this regardless of the type of addressing that it has or, you know, whatever. Yeah. So now this LDA immediate, going to get rid of the instruction, is an instruction that is an LDA, is an instruction, and uses immediate addressing. And the only thing we'll need to define is what bytes identify it. Cool. So similarly here, let's have a Again, I'm going to separate this out into separate files, but for now. So an STA is the type of instruction which means store in the A register. Oh, store from the A register, I should say. And again, so essentially what we're doing here is just implementing interfaces. Oops. And so its get data is going to be return the areg. And actually, an LDA CPU to areg equals value. Where does value come from? Get data. Because immediate actually does data. So that's why this was called an immediate read. Alright. Because you can't immediate write, I don't think. So this is immediate read, LDA, and instruction. We also want something that's an STA, which is just going to inherit from nothing at the moment, and it's going to say the data that we want to store is the areg, and actually we want it to inherit from something we're going to call like writable. So we've done this differently in the past, but no time like the present. So let's get rid of this writes to memory thing for now. I'm actually just going to copy this code out to something here, which is going to be a writes objects and the write method is going to, yeah. So the writes method is just going to implement something that can write to the CPU. So it's a writes to memory. Writes to mem. So an STA is actually just something that writes to mem. And gets the data from the areg. Cool, so this is how we're going to indicate some kind of instruction that writes to memory. Alright, so let's keep going then. Let's split this up into some new files. Call it generic instructions. Writes to memory is a generic instruction. This class instruction is a generic instruction. We're going to have to do some importing here and all that kind of jazz. Import this name and import CPU as C. We're going to have to inherit. I think these base instructions should probably just inherit from instruction. And then that way, LDA immediate can just be a construction of LDA and immediate addressing. And STA abs is just a combination of STA along with absolute addressing. You say your identifier byte. You don't need that because that's defined up here. Am I too late for today? No. I'm probably not going to be on I've been going for a couple of hours, I think, but no, I'm still going. How long have I been going for? Hour and 40 minutes. So, yeah, just in time, Black Stealth. Alright. I'll keep going for an hour or something, I think. This is all starting to come together. A little bit. A little bit. So I'm going to separate these ones into something that's not called generic, but it's going to be called base instructions. And this is going to, again, just be something that we import from here. Cool. There is also this. Did you start from scratch? I started from scratch. The KDEX is correct. Everything that you see here has been written on stream, and so you can watch it from the very beginning if you want. Because it's all up on YouTube and stuff. So yeah, see how it's all come together. Or starting to come together. It's maybe a better way of putting it. Alright. So a lot of these single instructions with implicit addressing are either set or unset a status bit, which is a pretty generic operation. And really, I kind of just want to be able to pass in what's the thing that you want to change. So someone, I actually can't remember who, probably KDEX was talking the other day about, instead of having all these registers stored separately, or at least the status stored separately and stuff like that, we should probably start thinking about putting it in dictionaries so I can kind of dereference it a bit easier, which is probably a good idea. Thank you, RegTM. It is a cool idea. I am not the person that came up with it. I am building on what other people have done. Which keyboard are you using? A Leopold high-end mechanical keyboard. I don't know. I don't remember. I bought it a couple of years ago. Dictionaries for registers. What? Yeah, there's some easier way of indexing that isn't directly linked to member variables. So I could reference them by key or something, which is probably going to make my life a bit easier. Yeah, that was you. Thank you, KDEX. Yeah, it's just I think, cherry brown mechanical keyboard, which is quite nice. I think it's called, it's a different brand in America. I can't quite remember though, to be honest. But if you look up Leopold keyboards, you'll probably be able to find out. Alright, what am I doing with my life now? Cool, so what I'm trying to say is that these status instructions are probably all going to be 90% the same code. So I'm going to set a certain flag to true or a certain flag to false. And they're going to have an identifier byte. Kind of like an array that has a certain size, type, and length. Yeah. Yeah. The difference being with dictionaries, of course, that you can index them by whatever you want. So you don't have to remember integers, for instance, like you would in an array to access an element. You could, store a string and then reference by that string. Yeah, which is the advantage of dictionaries. So you can pass around kind of nicer things to remember, like enum values or stuff like that. Yeah, sorry. Dictionaries might be Python slang. Alright. Let's just go with this for now. Whatever. Just absolute, CLD. This. So let's make all these things slightly nicer. Alright, let's import everything and let's see if this works. Do we crash where we expect to crash? We do expect crash. Okay, sweet. So we now have 4 instructions, which is pretty cool. We're still at the same amount of instructions, but we do have all the different types of addressing now. And you can kind of see that it's going to start speeding up quite a lot. Alright, let's do this then. So a base instruction is something that's going to set or it's going to clear a register. So let's say it's a set reg. It's going to be of a type instruction. So for instance, an SEI. Sets the register to be true. Now, actually, it might not even be a register. It's going to be setting a bit to be true. because you're actually setting a single bit out of a register. Yeah, so it's going to be setting a bit in a register to be true. But I won't. And then we're going to have a clear bit or something. But for now, so let's do def apply side effects, which is of course a class method. Cool, so the bit that we want to set is either going to be cpu.statusreg or cpu.statusreg.decimal bit equals false. So when it's true, we want to say class.bit equals true. And then in here, instead of doing all this kind of crap, we can just say bit equals CPU. No, because we need to know what the crap. We need to have a reference to the CPU. That's a pain, isn't it? Yeah, so potentially this is probably not a good idea, but we could just inherit from SEI, which is automatically going to, from a set or something. I'm just trying to simplify this a bit. So potentially we could say that we know that all set bits are going to have implicit addressing, and they're going to be built up from instructions, so they're not passing any parameters. And they're actually... So the only way we could really do this would be to say that bit equals... We could have like an enum or something where we pass in a string and we say like interrupt bit. And then over here in the CPU, it can know how to parse that string and which thing to flip, which I think might be kind of the way to do it. Right, so the bit is going to be the interrupt bit that we want to set. So an SEI is actually just going to be a set bit. The identifier byte is that, and the bit that we want to flip is the interrupt bit. So now here, in our thing, we actually want to say the CPU dot... Are we ever going to set something that isn't in the status register? Maybe not. So let's say status reg dot interrupt bit equals true, right? So this would set the interrupt bit to true. Now what we've actually got is that we've defined over here a string, and we want to be able to tell the CPU set whatever's got the value of this string to be true. So let's go to where we've defined status, which is back here. So instead of defining these as properties of the status class, we could define this status reg, instead of being this class, we could define it to be a dictionary. Or alternatively, this class could contain a dictionary, and I think I'm going to do that, so it's all contained in here. So let's say self.bits. You can make a registers class and pass a reference of the CPU's registers instance to every instruction. Thus, no instruction has to reference the entire CPU, but only to the registers. That's true. Probably, correct me if I'm wrong here, but the reason I wouldn't do that is because we need to reference the CPU in a lot of things. So we need to go through the CPU to find memory and to access all that stuff. And I believe that since we're not passing things by values, so we're only passing them by reference. So passing through the CPU shouldn't have a cost, right? Maybe. Excuse me. So I'm hesitant to pass through more things in the CPU as opposed to going through the CPU. But I'm almost certainly wrong, if that makes sense. but I don't know why I'm wrong. Hopefully that makes sense. So the reason I want to define this bit in the class is so that up here I can now do an internal class, which is going to be our status types, which is going to be an enum. So this is going to be a Python 3 enum, because they are now a built-in part of Python, which is super cool. Because I don't think that having a reference to the entire CPU is necessarily bad. KDX, I suppose, is my point. But I suppose you could pretty easily argue that it is from a what can touch what and mutability standpoint. Alright, so you've got your status types. So let's say that we've got negative. How do you define an enum in Python 3? Boom. Enum. Red, green, blue. Okay, I can't have capitals. Do I need to say equals 1? Equals 1. Okay. So we've got a negative, we've got overflow, interrupt. So this is going to be cool as well, because it's going to allow us to literally index things. So if we wanted to do that as well, it's going to be a lot easier by integer. So interrupt bit is bit 2. Decimal is going to be bit 3. Unused 1 is bit 4. Unused 2 is bit 5. Overflow is bit 6. Oh, this should be the 0 bit. And negative should be bit 7. And the first one should have been the carry bit. Right. So now we can do our self.bits is just going to be status types. We're probably going to have to status.status types dot carry. Now here's an interesting, can I just type carry? No. Okay. So we'll get our carry reference and we'll say we're going to set that to false. Alright, 0, interrupt. So this is going to allow us to reference things by whatever we want. Overflow and negative. Cool, so instead of doing this, so negative bit is going to be false, overflow bit false, interrupt. I believe it starts off at 34. Nestdev wiki. Let's find out. So the CPU has an initial state which gets set. Yeah, it's got a startup state, so we can see what the register is going to be set to. P34. So if I do 0x34 to binary, it's 1101. So the first two things are 0, then true, false, true, true. So it should be false, false, true, false, true, true, false, false. Always fun. Cool. Alright, so now those can all go. And now, do I use status anywhere else? No. So now, this can be called the carry bit. Alright. Oh, no, actually we can just leave it as that. And now in here, we can say the bit that we want to actually set is actually just status types interrupt. Nice. So now we can say which bit do we want to set, and it's a set bit. And then we can just have a non-set bit. What do you call that? Disable bit? I think it's called a clear bit, which is going to set a bit to be false. And so this is just going to be a clear bit. And we can just say the bit that we want to clear equals status.status_types dot carry. Is CLD the carry bit? No, decimal. Clear decimal. So that's pretty cool, right? So now we're getting to the point where we still only got 4 instructions, but you can kind of see that the code that you need to implement an instruction now is pretty slim. We just construct it using, you know, what kind of instruction is it and what kind of addressing does it use? And then this instruction is in turn just going to be built out of things like instruction or writes to mem and so on and so forth down the chain. So it just becomes really easy to construct all these functions now. So let's do that. Code optimize imports. Cool. So one thing that that did come up was this test ROM, which I was linked to. So I believe that this is it. Consider using NES test. Did that download? Is that what's going on there? Yeah, okay. There's a ROM called NES test. And start the PC at 0x0 and then see what happens. Alright, so let's do it. So this is going to be a test ROM, which is going to allow us to test all the instructions that are implemented in the 6502 and test that we're getting it right, which we want to do. So let's load this instead of our Super Mario Brothers ROM. So it's going to be uses Andrew. I'm going to duplicate this so I can say this is our test ROM. Uses Andrew, downloads. Ah, shit. Oops. User Andrew downloads and what's it called? nestest.nes. So we just need to load that ROM, which it's going to do, and we're going to chuck it so that it starts at 0x C00. Now down here we say equals self.rom.header size. So we kind of presumed that the ROM that we were loading in was a valid NES ROM, which it's not. So we're going to have to do a bit of dodgy stuff going on here. But mainly we'll just say, for now, instead of saying the header size is 16, the header size equals 0C000. Because that'll, yeah, that should do it. Alright, compared to a sample log. Documentation is here. Yeah, how to run it. Do, 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 do. Alright, so compare it to a sample log. Alright, so let's see what happens when I compare it to a sample log. Obviously, since I haven't implemented any instructions, it's not going to work, but kill me. Alright, let's see. Instruction not found. Fair enough. That is probably what we expected. looks out of range. Oops. Instruction not found. Empty string. Right, so what happens when we do this? So we might not have enough space for this to work in terms of how much space I specified for the ROM to have and the memory locations and stuff. Alright, so instruction identify byte self.rom and self.pcreg. So we're starting at 0xc000 49152, and we're saying that the bytes what's the length of the bytes? 24592. Well, that's not good. So that's, I don't actually know how this test ROM starts. Well, let's try open it and, see what happens. Let's test. Cool. Let's turn this into hex mode. Hey, it starts with NES. Oh, this is... Wait a minute. This is actually a valid NES ROM. Oh, cool. Nice. Alright. So our code will work. So shouldn't it start executing here? Oh. So we're saying that we're going to start executing at 00C 000. Yeah, which doesn't exist on this ROM. Am I crazy? Simply run it. Should be okay. I don't know. C 000. Can I search for 4C F5 C5? 4C F5 C5. 4C F5 C5. Right, so it's not at C00, it's at our normal starting point. Alright. Okay, let's see what happens if we start at a normal starting point. The instruction is none, and instruction is not found. Fair enough, because we don't know what that instruction is. Let's go then. So instruction byte 0. Let's turn this into... Wait, how do you turn byte dot from hex to hex? Hex. So what's the instruction that we're missing? 4C. Yeah, so that's the code that we want to find. Alright, so now we can just start smashing out some instructions. Ooh la la. Alright. 6502. So I actually quite like the Wikipedia page on this. Boom. Alright, so what do we need to implement? So it was 4C. So 4C is jump absolute, which is what we expect. Alright. Jump absolute. So here's what's going to have happened. We need to deal with offsets because the ROM, that memory address is 16 or whatever in the ROM, is 010, but is actually going to be mapped somewhere in the NES memory. If we look at the NES memory mapping, whoa. So the CPU memory map. So the cartridge space is going to start at 4020 and go up to FFFF. So actually, yeah. If a mapper doesn't fix FFA to some known back, typically along to the rest of the bank containing them, use some sort of reset. The vectors need to store in banks. I have no idea what that means. Whoa. Yeah, okay. This means nothing to me. Alright. Sickness. So what this log is telling us back here is that they expect to start at C00 and they see the instruction 4C F5 C5, which is a jump to C5 F5 because it's in little endian mode, which jumps literally to C5 F5. So that's probably what we want to see as well. So we need to figure out why our instructions don't start at C00 and why in fact they start at 10. And again, that's going to be that offset. C00 4C. Alright, well, let's just start by implementing a jump instruction. We can worry later about what all this kind of stuff means. I'm actually going to turn this back to the NES ROM. I'll figure out upstream. So, instruction not found, A2. Alright, let's implement whatever the A2 thing is. Bring that over here. So, A2 load X immediate. Cool. Alright, so in our base instructions, we need a load X instruction. Again, the cool thing is going to be that this is going to be the same as this, except with one value changed. We could genericize that, but that's fine. Load X, and it's going to be load X with an immediate value passed into it. So we're going to have load X immediate is going to be an LDX with immediate read addressing, and the byte address is going to be A2. Cool. There's another instruction done. That didn't work out because we need to register it. So potentially, the cool way to do this is going to be funky. Let's do instructions equals this. After finishing the emulator, you might want to write a NES decompiler. Kappa indeed. Yeah. Let's hope I can finish this. Alright. Let's see. Base instructions. So kind of what I want is something that'll, some kind of decorator here. which says register instruction. We want register instruction to be a thing here. Gonna have to figure out how to do class decorators again. Because I've forgotten how to do that. Bound methods, static methods, class methods. No, I want to create a decorator. Nope. There was a good page that I read last night. I'll have to find it. Yeah, this is it. Class decked, init. Class decorators. Yeah, this is what I want. Alright. So we want a class registry. We want to just call this instructions. And instead of instructions mapper, yeah. We just want instructions to be a dictionary, and we want to say instructions class.class ID equals class. We actually want to get it by identifier byte. Return the class. So now when we call the @register function, they'll be loaded into this instructions object. We can get rid of all this crap. Now when we're down here, we can just call instructions. Let's see what happens if I do that. So instructions now should just be LDA immediate mapped by A9. Yeah, nice. And identifier byte is a byte. Sweet. So I'm going to put this stuff in generic instructions. Because I'm crazy. Oh, pep it. Alright. So now, when I call register, let's just make sure we optimize these imports. Instructions. Cool. So now when we call register on each of these things, it's going to register like that. Accepted 2 blank lines, found 1. Alright, so now when we come in, it should be able to run until it finds a new instruction, which it does, 7.8. Alright. So this is now going to be what we do, but instead of doing it one at a time like that, I'm just going to pull this up here. I'm going to put this on this side. I'm going to put this on this side. I'm going to find wherever the 6502 wiki page is. And I'm just going to start smashing through some of these instructions. Boom, 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 show. Alright. Cool, that's the thing. And this is this thing. So let's just start getting some easy ones done, because this is going to take a while. So let's start doing this A row here, and we'll just start working our way through them. So A0 is going to be load Y. I don't have a generic load Y instruction yet. So let's say load Y is going to change the Y reg. Oh man, I'm tired. Load Y is going to change the Y reg. Yeah, it's going to have to be a bit different. Alright, give me a second, sorry. Alright, sorry about that, just checking on some dinner plans. Alright, so we've got a load Y instruction, which is going to take a Y register. And yeah, keep going. So let's register a load Y immediate. Load Y immediate, which is going to inherit from load Y and is A0. So A1 is going to be load A ind X. Now I believe, unless I'm mistaken here, that this is indirect indexed or indexed indirect. God. So we'll head back to our decompiler page that explained what the different types of indexing were. Instructions, addressing modes. So the one that we're looking at here has got ind and then both of them in brackets. So it's indexed indirect. Yes, so, alright. Which one was it? Indexed indirect. God, okay. So there's a load A. So we're going to have one here that is a load A indexed indirect ind, and it's going to be indexed indirect which is actually indexed indirect addressing. Nope, I want to import that. Alright, and that's going to be A1, load A. Yeah, so you can kind of see how this kind of stuff is going to come together. This is just going to be a lot of grunt work, basically, of typing these out, but it's just composition now. We're not going to need to write code for any of these, which is pretty nice. So I might do A registers. So, well, let's just do load A. So let's do all the load A's. So we've got immediate, indexed indirect, load A, 0 page, so on and so forth. Alright. So the 0 page of LDA is going to be 0 page addressing along with an LDA. It's going to be A5. LDA immediate we've got is A9. LDA absolute is AD. Abs is going to be absolute addressing in LDA. It's going to be AD. And then B1 is going to be LDA God. LDA indirect indexed, kill me, is going to be indirect indexed addressing. It's going to be LDA, and that's going to be B1. LDA Z package 0 page with X. Alright. So there's kind of going to be a trend that's going to appear here, which hopefully we can make generic. But 0 page X, which is 0 page with X addressing, I believe. I'm wrong. 0 page addressing with X. Sure. And this is going to be B. God. Where am I? B4? I'm losing it. It's here. What's this? This is B1. No? LDA, this one. What's this one? 5. God. B5. Alright. LDX Z package with Y. Alright. Y, B6. Let's import that class. Oh, actually, LDA Z package with Y is somewhere else. Maybe you can't even do it. So that's LDX. Alright, so LDA absolute with Y is A9. B9. LDA absolute with Y, okay. Whew. LDA absolute addressing Y offset. Again, I can standardize all of these later. LDA abs Y. Is going to be B9. Can I see any others? Yeah. LDA absolute X. Alright. So the point of doing this once is that I then want to be able to genericize this for other classes and do something really dodgy. BD, where we like, hello, Wime. Why me? Or Wime. Welcome back. Okay, is this all the LDAs? How many do I have? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 9 in the example code. Nice. How's the keyboard grind going, Jay? It's gone really well, actually. I'm probably pretty close to tying up, but basically got all the addressing modes in. There's one bug that I know about, but they're all reasonably generic and composed. Cool. I've got some base instructions now, like LDAs and LDX and set bit things. So basically, this is what the instruction file looks like now. So this is how we can declare like a load A with immediate. You just say it's a load A with immediate. I would say cool is definitely my favorite word. I use that one a lot. Yeah, so this is like all the LDAs. I'm hoping that we can genericize this into something that will then be able to spit these out using some Python 3 metaprogramming fanciness. Yeah, cool. Cool. That's a cool word. Whoa. What did I do now? Alright. OS X. Let's get rid of all this stuff. There's another word. Oh. Did I break that? I did. That's okay, whatever. They can all go in one line. Yeah. I'm gonna finish it up there. Actually, I'm pretty done. Hit a point and you kind of brain explodes. Cool, alright, dodgy, genericize. I think that's probably the order as well. Looks marvellous, thank you very much, why me? Much more fun than the keyboard grizzle I was on for uni yesterday. Yeah, how'd that end up going? It was Java stuff, wasn't it? Looks good to me. So there's still plenty of stuff that we can do here use to make this more generic, which is my favorite word, but I'm really happy with the progress we made today. We didn't actually get that many more instructions done, but all the addressing mode's been done. You can see just then it's going to be pretty quick to be able to add all the instructions that are left. Seeing as how now you just need to compose them out of like two things and say what's their identifier byte. Cool. Adding all the addressing modes and more instructions. Done. Can I tag in source tree? That's a great question. Tag. I don't remember what my tags were like. Okay. Episode 4. And push the tag. Holy moly. I am fried. Alright. Yeah, this was really good. I am going to leave it there. I'll just check that that's pushed up and that Git isn't messing with me. I'll kind of reply to this issue soon. Dan. Last commit a minute ago. Nice, that's awesome. Sound on mute. I'm just finishing up, unfortunately. Seeing as how you probably can't hear me. Yeah, so I don't know if anyone has any questions or whatever, or thoughts about what's going to go on next. I think it kind of became a bit more clear today what this is all going to all gonna do. Seems good indeed. Great work today. Thank you very much, Katex. Thank you, Dudita? Huh. Dudita. Yeah, it's been good. I think you can kind of see how this compositional style is hopefully going to come together and make things a bit easier. Yeah. I'll need to figure out. I probably need to have a things to do list so I can remember. So one of them is going to be offset for ROM, because when we're doing jumps and absolute, we'll need it to be where it expects to be in the memory. There's still a bug in addressing, which I need to figure out, to do with offsets for indirect. Kappa. What else? Oh yeah, all the instructions. I want to make something that's going to spit out all the different modes of instructions. So using Python 3 metaclassing or something, because this is why I wanted to do it with classes, so when we get to this point, we can start doing some really dodgy Python stuff. Dodgy, yeah, I'm using my buzzwords. We can use some code that's going to give us all those different classes automatically and add them all and construct them for us. So I wonder if we can do that so that we don't have to manually type out everything, because I don't like typing. I want this to kind of be pretty compact and look reasonable. Spit out all the addressing type classes, because they don't do anything except inherit from a different addressing mix-in, so it should be possible. Yeah, that's all the ones I can think of off the top of my head. Anyway, thank you very much, everybody, for tuning in. I will be back at some point. Probably not tomorrow. Maybe on Wednesday. I'm a bit unsure at the moment. I got a bit of stuff to do, so. Oh well, we'll see. This will go up on YouTube, obviously, and yeah. I will see you all next time.